All right, we're going to talk about position, velocity, and acceleration as functions of time. This is section 3.4. Let's start our PowerPoint. And here we go. Let's look again at the relationship between simple harmonic motion and uniform circular motion. Not yet. Look at the figure, which shows a ball on the rim of a rotating turntable of radius A. We'll call the circle made by the ball the reference circle for the motion. Let's assume the turntable revolves at a constant angular speed, omega. As the ball rotates in the reference circle, you can see that the angle theta made by the line OP with the x-axis changes with time. At the same time, the projection P on the x-axis, labeled point Q, moves back and forth along the axis with a simple harmonic motion. Let's see, from the right triangle OPQ, we see that cosine theta equals x over a. So that means that the x coordinate of the ball is x equals a cosine theta. Because the ball rotates with constant angular speed, we know the relationship between theta and omega. So we can rewrite our expression for x. X equals a cosine theta omega t. In one complete revolution, the ball rotates through an angle of 2 pi radians in a time equal to the period t. In other words, the motion repeats itself every t seconds. Therefore, we can write an expression for omega as shown. Omega equals delta theta over delta t, which is 2 pi over t, which is equal to 2 pi f, the omega. We can write the expression for omega as shown, where f is the frequency of the motion. The angular speed of the ball as it moves around the reference circle is the same as the angular frequency of the projected simple harmonic motion. So we can also rewrite our expression for x as shown here. X is equal to a cosine times a times cosine of 2 pi f over t. We also write that as a cosine omega t. Okay. This cosine function represents the position of an object moving with simple harmonic motion as a function of time. The top figure shows a graph of this function. Because the cosine function varies between 1 and -1, x varies between a and -a. The shape of the graph is called sinusoidal. The middle figure represents the curve for velocity, and the bottom figure represents the curve for acceleration, both as functions of time. Here's the equation for the velocity. Here's the equation for the velocity. V equals square root of plus or minus square root of km times a squared minus x squared. I lost my place. Okay, let's combine equations. Okay, now we can make use of the trig identity and make substitutions. I won't require you to do that. We get this result. We don't need the plus and minus sign anymore because the sign can take both positive and negative values. So the velocity is equal to a minus a omega sine 2 pi ft. Now, for those of you that know calculus, if we write x equals a cosine omega t, you'll see that the velocity is the first derivative of a cosine omega t, or so v is equal to minus a omega sine omega t. If you don't know calculus, that's fine. You don't worry about it. Okay, to derive the equation for the acceleration, start with the position equation and the equation for the acceleration, which we derived from Newton's second law. Combining equations and substituting omega squared, we get this result. Okay. Notice that when the displacement x is at a maximum, at x equals a or x equals minus a, the velocity is 0. And when x is 0, the magnitude of the velocity is a maximum. Also, when x equals plus a, its most positive value, the acceleration is a maximum, but in the negative x direction. And when x is at the most negative position, x equals minus a, the acceleration has its maximum value in the positive x direction. So you kind of have to look at these graphs at the same time. I think I might show another Walter Fent equation. I may not have it. If not, I'll just go on to the next section. Let's see, am I done with this section? May not be. No, I have one more slide. Okay. Take a look at this figure, which shows one experimental arrangement that demonstrates the sinusoidal nature of simple harmonic motion. An object connected to a spring has a marking pen attached to it. While the object vibrates vertically, a sheet of paper is moved horizontally with constant speed. The pen traces out a sinusoidal pattern. You also saw this in the Walter Fent video. As the spring went up and down, you saw the sinusoidal form on the side. Okay. Let's stop here. Next, we're going to talk about pendulum, motion of a pendulum.